to meet you here. I am very happy that you could came this first week of the year. It's not an easy time to do this thing, but this is the beginning of a 2 months research, teaching, and other things project, and it's very interesting for us, for the Singularity group to be here, okay? So thank you very much for you to accept this invitation and to be here, okay? Thank you very much. Okay. And now we will begin the Congress, and Juan Ho is going to do the first, be the chairman of this talk. And by coincidence, I am the first speaker. Not only by coincidence, but because of some travel details of several people, I decided to be the chairman because I was sure that I should be here this first time, okay? Thank you.
Okay, so thanks, Marcelo, and it's my great pleasure to be the chairman of this morning session and to introduce the first speaker, Professor Marcelo Saya from the ICMC from São Carlos, and it's a mini course, no?
It's part of a mini course and a talk.
Okay, so it's
the
about,
first is both.
So the first talk about multiple point sets and real good deformations of map germs.
Okay. So as I told you, this should be the third class of the mini course, of the course, not mini course. But I put it in the first talk because of some conditions, and then the students that are going to do the course will see these things again during the week and during the next month. And I am going to talk about a joint work with Audicio Miranda and Tassiana Oliveira. They are from University Federal of Uberlândia. This second part of the talk. And I am trying to do some kind of panorama on the work that I've been doing along of this time, okay? And then I am going to talk about multiple point sets and later on real good deformations of map germs. The multiple point sets, as we can see in the bibliography, is the most important are the most important sets that we need to see to understand the invariants that we need to classify map germs or germs of functions on these things, okay? So beginning, just an introduction, as you know, the singularity theory officially began with the work of Whitney, and then Thom, Arnold, Morse before. They did a lot of work, Arnold and Thom in the 60s, 70s, Morse before Whitney in the 50s, to describe the general situation of classification singularity theory, okay? On the other side, the numerical invariants, they are my favorite tool to understand and to control conditions of singularity in some situations. They are very, very interesting. So I am going to give an overview about these things, okay? And the first thing are the stable deformations of the original map. And just some example. This is an example that I believe that you have seen before. I have been using these examples in several talks and courses, mini courses. And there is a very small book of Varchenko, of Arnold, The Zoo of Singularities. Very small. In fact, I bought this book here in NIMPA by a situation that I couldn't believe. Oh, let me see. But you can see any book of Arnold, even of Varchenko, they always describing these examples. And these examples are very, very interesting to see what's going on, okay? X3, you really know how to do the graph of X3, and you really know that it has only one singularity, the origin. So, can you see here? It's okay? Of course, that this is not the correct, but singularity here, okay? Only one singular point, in fact, only one critical point. The singular point I call the image of the critical points, okay? Just to do some difference. Now I do a deformation. X3 plus Tx. When we do it, if you fix some t, you have ft. And we have clearly two. It's critical points. So, from x3 to x3 minus tx, we exchange the map for every t fixed, and we have two critical points now. In real case, a maximum and a minimum. So, we say that the origin of the original map splits in several critical points, okay? This is the main idea in singularity theory. If you want to see what's going on with a map, do a stable deformation of this map, and then see what appears. If you do the same thing for the map X5, you can see clearly that you are going to have 4 critical points, and not only 2. So we can, but if you look for the first map, has just one critical point in origin and nothing else, okay? This is the main idea in singularity theory. You need to see what's going on with a stable deformation of the map or of the function to see the origin or why they are different, the maps, okay? So when we are going to talk about invariants or even classification or something, we need to look to the stable deformations of the map, okay? Another example, just to say the difference between stable and non-stable maps. This is clearly not stable because you do a small deformation and it changes. Sorry. If you have to wait for something that is stable, you can deform it around it in some topology, the Whitney topology, or even other. You see the difference. If you consider the map x2, the function, okay, there is one critical point also, but when you consider deformation x2 minus tx, I did the same deformation for different map, but doesn't change the critical set. Of course, that this is not a proof that this map is stable, okay? But just an example. If you can do any deformation around the original map, and it does not change the critical point, you can say, oops, there is something that's the same in there. This is a stable map, okay? When we are going to work, we take the map, we deform, take a stable deformation, and see what will appear there, okay? And then this is a typical example of a stable, and the other is a non-stable function. Okay, now I am going to talk a little bit about invariants. Not all invariants. Why? There are others, of course. Another very important invariant, I am not going to talk about it, is the Turina number. The Turina number is a little bit more sophisticated than the Milnor number, but is much more complicated to work. So it's my favorite, the Milnor number. 3 different definitions of the Milnor number. There are others, yes, but these are the most important for us, okay? There is the first deformation is the number of, this is for functions, okay? Germs of functions, the Milnor number. We we'll see other Milnor numbers later, the discriminant Milnor number in special. But this has three definitions. The first one is really the first one. You deform the germ, you see how many stable singularities appear. As we are talking about function germs, the stable deformations are Morse points, okay? Morse points, I believe that you know. If you don't know, it's a sum of quadratic. It's a quadratic form, okay, with signals, but the Milnor number doesn't count the signals. But in general, what happens is when you do the stable deformation, you count the number of singularities, of critical points that we found. Okay, there is an algebraic version. It's my favorite to work because it's an algebraic. We have other conditions to do with algebra. And the Milnor number is the dimension, the dimension of that algebra. On is the set of all function germs in that situation from Cn, considering the origin, going to C. And there is another version that is very, very important also, because we can do this definition for other situations using the third definition, is the number of spheres in a bouquet. Okay, a bouquet or edge. What is this? Okay, you take a deformation, consider the inverse measure of some ft, and the inverse measure, you see a bouquet of spheres. If you see a bouquet of spheres, you count the number of spheres to see how many spheres you have. Then you have the Milnor number is really the number of spheres, okay? Later I'm going to talk about the Milnor number, but on the discriminant Milnor number. Just to remember, if we go back, here I have one critical point in any deformation, so the Milnor number is 1, okay? And on the other example, the Milnor number is 2, okay? Because you have 2 critical points in the stable deformation of the germ. Good. A very, very important property of the Milnor number is that the Milnor number is a topological invariant. In which sense? Okay, I'm not talking about 2 different germs. Oh, this has Milnor number equal to this. Then they are equivalent. No, I need to have a family to be sure about this, okay? There is a quite different situation when you look just for 2 germs. But if you look for a family, and in this family, the Milnor number is constant, so they are homeomorph. In this situation, the germ AGT, oh, I found it, the red light. The germ AGT here is an homeomorphism in the source, okay? It's the right equivalence, okay? But it's homeomorphism because it's a topological, we say that's a topological invariant because of this, okay? Milnor number is also analytical invariant, but it's more important because it's a topological invariant. Now, we go to the other situation. I'm not looking just for function germs. I'm looking for map germs. Oh, good. What happens with map germs? P is bigger than 2. The target space is not just one-dimensional. It's more dimensional. We are in the same situation. We look to a map germ from Cn to Cp, from the origin, around the origin. Okay, it's a germ. And then we look to the singularities which appear. But any singularities? No. We look for the singularities which appear in a stable deformation. They are called stable singularities because of this, okay? How can we study the stable singularities? This is the K2, as I told you before, the multiple point spaces, okay? These spaces are very, very important to study the singularities. When I talk about singularities, I am talking about the image of critical points, okay? I am in the target. And in the target, we have the image of the critical points that I'm calling the discriminant. And then we need to study this guy, the discriminant of a map germ. So we do the stable deformation, we look to the discriminant to see which singularities appear. Okay? First example, not example, but the historical situation. This was really considered the first singularity theory article, okay? 55 by Whitney on singularities of mapping on Euclidean spaces. Before this, we just had the results of Morse talking about the Morse points which appear in a stable deformation, okay, of a function germ. Now I am talking about a stable deformation of maps. So, to go from Cn to C to something else, we change. Okay, C2 is the first step, okay? From C2 to C2 is really the paper of singularities of mappings on Euclidean space. You don't see germs here because they are, Whitney was talking about general situation, but considering local case for every singularity that he has, okay? Which are the singularities that appear for map germs, for stable map germs from the plane to the plane, okay? The stable singularities are cusps and double points. This is the most typical example. I have been using this example all my life. Here it's quite, I have a blue point here, other blue point here, two green points here, okay? And the images of these points by F, okay, this is the map F, y4 plus xy minus y2. I have this point is the image of this green point. This other green point is the image of this green point. And these 2 points here go to form a double point in the discriminant, okay? In fact, here the discriminant is the red line, the curve, okay? This is the critical set. And we have, for this situation, one double point is a transversal crossing of points of first type singularity, A1 singularities, and two singular points that are the cusps. These are the cusps of this map, okay? So here we have two cusps and one double point, okay? These points are very important to describe the map. Just to complete this example, in the critical set, this is a smooth curve, and this is not a smooth curve, of course. And then the discriminant curve, the image, has two cusps and one double point, okay? And Gaffney was one of the first guys to study this after Whitney. Gaffney is much more younger than Whitney. And he gave a formula to compute the numbers C of F and D of F. C is cusp points, D is double points, okay? In this situation, we can see clearly that the discriminant is homotopic to a circle. I am going to talk about this homotopy type later, okay? But just remember now that this is important to describe the topology of the discriminant, okay? Good. This is the article of Damon and Mond, okay? Now I am going to talk about discriminant Milnor number. The discriminant Milnor number is a number associated to discriminant, okay? Why it's called Milnor number? Because of the third definition. Where is the third definition? Here, of this topological definition. Damon and Mond showed that the discriminant in this situation that I am describing here in this paper also has the homotopy type of a bouquet of spheres, of a wedge of spheres. So everything in singularity theory that is homotopic to a bouquet of spheres can be called the Milnor number. Okay? I remember that I was very young. I was doing some work with Ballesteros, and we called the Milnor numbers for other things, the number of a different number. And then Ballesteros gave this talk in São Carlos, and David Monio was in the following the talk. After the talk, he told, oh, you cannot call this number as a Milnor number because it's not a bouquet of spheres. So we need to be careful about this. If it's Milnor number, for bouquet of spheres in some situation. Okay? In this case, the Milnor number of the discriminant is a bouquet of spheres. So if it's a bouquet of spheres, you can call it discriminant Milnor number, is given the definition here in this paper. This is a very interesting paper. I didn't read this paper carefully, but I know that it's very interesting. We use these things, but we have no time to read everything. I would like to have. Maybe from now on I can go back and read. In fact, I started to read the first article, this, on singularities of maps of Euclidean spaces. I always talk about this paper and never read it before. I began to read it 2 months ago. Oh, I need to read it. So I did, but I didn't read yet because I didn't have time. I needed to prepare everything for these meetings. Okay? But we can use it. Example. This is a very interesting example. It is really in this paper, and you see why it's interesting. The map germ from C2 to C2, fxy, z6 plus xz, zeta, sorry. So we take a stable deformation, z6 plus x zeta plus y zeta 4 plus v zeta square. This guy has the homotopy type of a wedge of circles. How many circles? 6. Wow. How can we see this? This is the discriminant of that map. Okay? Here we can see 1, 2, 3, 4, 5, 6 double points and 3 cusps. Okay? Is it stable? Because it has only a singularities, these kind of points. And this is really a bouquet of spheres. How can I see this? I hope that it works. No, it's not here, but here. Oops, didn't enter. Sorry. I can show you later, okay? You can transform this by homotopy in 6 circles meeting in one point. I have the film of this, okay? But it's not appearing here. Probably I did a mistake from the computer to the pen drive, okay? But I can show you later easily. So here I have 6 circles meeting in one point. So it's a bouquet of 6 circles. Just to say something else, 6 double points and 4 cusps. Oh, there is the 4th cusp here. Okay? And this click should appear the film here, but did not appear. Okay. Now we go from map germ from R3 to R3. Okay. Why not from R3 to R2? As I am talking about map germs. Okay, if I go from C2 to C2, if I go from Cn plus 2 to C2, the singularities which appear are the same. Okay? They don't change. The stable singularities. Okay? The kind of singularities. So it doesn't matter what happens in the source in this situation. If you fix the smallest source that you are considering from R3 to R3, here I can talk to you that for this situation from C2 to C2 or from R2 to R2, you can add more variables in the source and just add zeta 2 more variables with square variables to be stable. You don't change the singularities that appear in the target, okay? So we don't need to look to more than dimension 3 here to understand the singularities which appear in a stable map in this situation. Very good. What are the singularities? This is the traditional swallowtail, okay? Rabo de andorinha in Portuguese. This is a monogerm, just one point going to this point, okay? This is a bigerm. This is a cuspidal edge crossing a plane, okay? So this is a point A21. These numbers which appear in this notation, as far as I know, were given by Arnold, okay? If I am wrong, please tell me if you know a better reference, but I think that was Arnold who gave these names. This is the swallowtail, okay, the rabo de andorinha, very traditional. This is a double point, a crossing between a cuspidal edge and a plane, and this is a triple point, okay? Triple point, transversal crossing between three planes, okay? So I have one triple point here and this situation. These are the zero stable singularities which appear in the target of map germs from R3 to R3 or from C3 to C3, okay? It doesn't matter if you look to the real or the complex case. As I am writing below, from C3 to C3 is better. When you consider the real case, you have these singularities, but some of them can disappear because of the complex situation, okay? Stable singularities. As I told you before, these are the zero stable singularities. Why zero? Because they are zero-dimensional. They are isolated points. Very natural to call zero stable singularities. As far as I know, this kind of name was given by Gaffney. At first, I saw first in the papers of Gaffney. I don't know if other papers before, they are called zero stable, one stable, or two stable singularities according to the dimensions of target and source, okay? Here we have the stable singularities, one-dimensional stable singularities. Here we have a cuspidal edge, okay? And here I have a double point curve, okay? This, for map germs, from C3 to C3, stable map germs, one-dimensional singularities are only these two that can appear, okay? Maybe they cannot appear. Clearly, you see here only cuspidal edge, okay? This is a very nice picture that we can describe some things. I will use this picture later also. Here I have the discriminant, green point, swallowtails, white, a yellow point here. The yellow point here is a crossing between a plane and a cuspidal edge, okay? So this is a point A21 in this example. This is a swallowtail, and this is a swallowtail. This map germ from C3 to C3 is stable. It has two swallowtails, one point of type A21, double point crossing between a cuspidal edge and a plane, okay? And here I have the critical set, okay? The critical set here is in C3, okay? I am just looking the source and target C3, critical point is a two-dimensional, smooth critical point, critical set, okay? And here we have some curves. This is a blue curve. This blue curve here goes to this cuspidal edge here, and the red curves here go to a double point curve, okay? This is very, very important to describe the singularities of the discriminant, okay? But I cannot look just here in this situation Because, okay, I can. Just from C3 to C3, it's easy to see an example, but when you do a general case, to look at the critical set, it's quite more difficult. But there is the situation that I'm calling multiple points. This is very well described by David Monde in some articles and some short courses that he gave here in Brazil already, in São Carlos and in Salvador also. Now we have a very special situation. First, I have a plane here. Why a plane? Oh, the plane is just the critical set. So you project the critical set in a plane. And then we have two curves, the red curve and the blue curve. And you go to discriminant, the same. But I'm going from C3 to C3, okay? This is a Cohanque-1 map germ, okay? If it is a Cohanque-1 map germ, the first two coordinates from C2 to C3 are the identity, x and y. So we don't look to multiple points that are the same, so we are looking to different kind of points. To do it, we double, triple, how many sources we need? Oh, I'm going from C3 to C3. Okay, I go to C3 times C3 and play the same thing. I am just extending the stud in the source to some space that's have more dimension, bigger dimension, but we split the critical point, the critical set, in a situation that you see the points different. Here I have just one critical point. When I go here, I have other two going to this guy. Of course, it's a crossing. If it's a crossing, there are two guys, okay? I am just putting these points away one from the other to understand. This is real, the multiple point set. So I do copies of the source, and I split the singularities which are crossing down, and I see a different kind of sets, the multiple point sets. Then I am going to describe this discriminant looking to the multiple point set. The multiple point set gives all informations that you need to understand here, but in a more clear situation. Okay, I have 1, 2, 3, 4, 6 yellow points here, and the other two green points here. And here they are mixed. It's more difficult to understand. Now I have different situations. Any of these guys are isolated. There is a blue curve here. The projection is down. A red curve here. So I can study easier this guy than this. Oh, but the dimension is bigger. Yes. Why C3 here? Because of Cohanque-1 situation. Okay? If it's not a Cohanque-1, here should be a C6. But in the map germs, the non-Cohanque-1 situation, there is not so many things done. Okay? This is the formal definition of multiple point spaces. This definition was given by Gurionov and Monde. First by Gurionov, later by Monde and Gurionov. Okay? This is, in fact, a way that I did with Victor Hugo after the works of them to describe these guys. Okay? Oh, I am going from Cn to Cn in this situation. Okay? You can do it in any dimensions, but this is just from Cn to Cn. And then we describe the number of multiple points, DLFP. P is a partition, okay, R1, RL, of any integer smaller than n. I'm talking now. This kind of definition was done first in a paper of Maria Ruas, Tom Marar, and I forgot. Oh, Montaldi, yes, and Montaldi, for the zero stable singularities, okay? Then we did the same definition, but not just for zero stable singularities, but for any dimensional singularities. It does not appear here by now. What I'm doing here, Cn minus 1 times Cl. Cn minus 1 are the first n minus 1 coordinates that I'm not changing. You can see this x and x here. This is defined as the cohunc of the map germ. This is a cohunc 1 map germ, okay? And then for any double point, triple, quadruple point, you include one variable more to see the difference. Okay, so I am considering a map germ from x, z1, z2, going to something else. And z1, z2, you can vary these guys. You just cannot put both together, because if they are both equal, if they are equal, you have no double points. So we need to consider zi different of zj, okay? And look to the guys which have the same image, okay? But as I showed you in the examples, the kind of singularity can be different, okay? Not the same kind. If you go back here, this is, the other is better. A singularity that has A1 singularity, that's the plane, and the A2 singularity, which is the cuspidal edge, okay? This is a point A21. You see this notation, it's clear that I have a transversal crossing between a cusp edge and a plane, okay? This is a point A21. If you go in the general situation, you have a DLFP, okay? L is the number of multiple points, 2 double points, 3 triple points. If you go to bigger dimensions, you have other things. But, oops. Yes. But any of these points that appear here, x, gj, have a singularity of kind arj. Okay? Just to describe the stable multiple points, as I showed in the pictures of the example, if you consider just the partition P equal to 3, okay, we have the traditional sigma 1, 1, 1 of F critical point here, okay? This is the notation that I'm using this notation here, okay? This is a D1 F3. D1, oh, if it is a D1, it's a monogerm, okay? This is really the critical point that gives you a swallowtail in the discriminant set, okay? If you go down, if you take the partition P equals to 2, 1, I am just considering the partitions of the number 3 because n is 3 here, okay? I'm going from C3 to C3, and I'm looking to the zero stable singularity. So I have to do a partition of the bigger number in the source. D2, F2, 1. Okay, I have a double point here, but a crossing between a singularity of type A2, that's a cusp, a cuspidal edge in this situation, and a point that's a singularity A1, that's a plane in the discriminant. Here, F has a singularity type of A2 in X, Y, Z1, okay, because of this notation, and the singularity of type A1 in X, Y, Zeta 2, okay? So the image is a B-germ, is the transversal intersection of a plane with a cuspidal curve denoted by A21. As I showed you before, here, okay, we have these guys. But when I go here, Cn minus 1 times Cl, I am here in this big space, okay? Here I am in C2 times C2. C2 is because xy, the other C2 is because of double point. And the triple points are denoted in D3F111, D3F, a set of triple points, okay? This is the image of the singularity. How can we compute these numbers, or these multiple point sets? First, we developed some things to work from Cn to Cn and to compute the multiple point sets in the source. Marar, Montaldi, and Cidinha. I didn't remember, but I had it here, okay? They wrote the paper, multiplicities of zero schemas, and zero schemas are zero singularities, okay? In quasi-homogeneous Cohank-1 singularities. Very, very interesting paper. They gave a formula to compute the singularities in terms of for weighted homogeneous germs, map germs. Very nice formulas. And then I developed with Vitor Hugo and Daniel and with Audicio also. Here I have the description of the zero schemes. Here in this paper we have the description of all schemes, any dimensional scheme from Cn to Cn. Okay? And Miranda developed his dissertation of master in this situation from Cn to Cn, but only the sources. This is the dissertation in Portuguese. It's in the site of ICMC USP, and this dissertation describes the results that are given here with details, and very nice to learn how to work with these guys. Now, we need to compute these guys in the target. Here it's a very, very problem, a very, very difficult problem. How to compute the discriminant? It's not easy. You can do it by computer. You cannot do it by hand, unless that you do for very small dimensions and for stable singularities. But if you do in any dimension, in any situation, you need to work with the computer to do these things. How? So we need someone that is really an expert in to do softwares for these things. This is already what the main work of Audicio. Audicio was my student and a student of Vitor Hugo. He developed techniques all his life to compute discriminants and to work with discriminants. There is the usual, traditional way to do these things that is described in a PhD thesis of a student of David Monde, Diana Ratcliffe. But if you look to this PhD dissertation, you only see very, very small examples of very easy guys to look to discriminant, when the discriminant is already very, very easy to compute. It's not, we read this thesis, we read it already. The theory is fantastic, but the practice is not so easy, okay? But Audicio, together with me, we developed. The main problem is to compute the discriminant. We need first to compute the presentation matrix associated to the discriminant. We did it in this paper. This was quite a fantastic result, but for Cohank-1 map germ from Cn to Cn, but just for this situation, okay, but only this situation is what we have done. Here we have something more special, was developed much before. This article, we discussed this article walking in Teresina, Piauí. We were visiting Humberto and Liane, they were my students. We stayed there for 1 week, and after working, we went to walk around the river in Teresina, a very beautiful place. And then we began to talk. Of course, we are always talking about mathematics. We sleep thinking about mathematics all the time. My wife says this, you only think about mathematics. Not only, I think about you also. So but during this walking together, we were talking about this, and we can do the presentation matrix for this situation quite easily. So we wrote this paper 30 days to write this paper, then to do the corrections 1 year more. But the idea was just when we were walking, talking about this. Later, Audicio, Marcelo Hernandes from Maringá, Guillermo Penaforte Sanchez from, now he's in Spain again. And they developed an algorithm to compute the presentation of push-forward modules. Here, I don't have just a Cn, but you can have singularities from x0 to Cn. So you look to the discriminant here, go back, look to the inverse image, okay? This is the push-forward modulus, okay? They developed an algorithm to compute the presentation of these guys, okay? Very interesting paper, not easy to read, but it's very, very interesting. This is easier to read and easier to use also. Now I am going to the second part of my talk. This was the first part. The students that are here, so yes. The meaning? You have a matrix. You need to develop a matrix which gives any information that you need for the discriminant, and much more. You look to the fitting ideals of this matrix to look to the discriminant.
But its matrix presents what?
The
What is the idea? What information is there?
The information is for to compute the fitting ideals. Okay? This is the matrix that you need to compute the fitting ideals. Okay? We are considering these constructions just one fitting ideal. But if you have a Cn times Cn matrix, you have more fitting ideals. Okay? And the fitting ideals describe, I am going to show you probably next transparency. Because if you look to the fitting ideal, you compute the fitting ideal, you have a number. This number describes the sum of all singularities of zero stable singularities that appear in the discriminant. That's the point.
So what is the size of this matrix?
I have no idea. What do you mean?
The size means...
The size?
yeah, size.
Oh, from Cn to Cn is a matrix from a n by n matrix. N by n matrix. In this situation, okay? Okay? Good. Now I'm going to talk maximal and good real deformations. This is what we are going, this is a work in progress, okay? I didn't finish. The motivation to do this came from the work of David Diamond. And not only from the work of David Diamond, but the motivation to develop the theory, because he described a very natural way how to compute the multiple point set in the source. And from this, we describe the other things. But what is maximum and good real deformations? A very, very interesting question done by David Diamond. We have the definition of a maximal or M deformation. Now I am comparing the real and the complex case. Okay? In the complex case, I know how many singularities and which type of singularities I have independent of the situation. If I go to real case, maybe some singularities disappear. Okay? If they disappear, we don't know what's going on. So David Diamond gave this question. What? We have a maximal or M deformation, a real, okay, from Rn to R0. This is not this only situation. You can do it in different dimensions here. But I am talking in this transparency just for Rn to Rn. It's called maximal if it exhibits all zero-dimensional stable singularities present in its complexification. Okay? Zero-dimensional stable singularities are the zero singularities which I told before. It is maximal from Rn to Rn. We can see all singularities, complex singularities that appear. This means that all singularities are really real. There is no complex singularity. And there's a good real deformation, a much more complicated definition, because here I am talking about the homology of the discriminant, of the discriminant. This is the discriminant Milnor number that I told you before, okay? It's a good real deformation if the image is the same than the complex. The homology is the same, okay? Sometimes we have a bouquet of spheres. In the complex case, you go to the real case, the number of spheres is less than the initial because some of them are complex, you don't see. So David Diamond developed this theory, and they also did this very, very interesting question. It's true that every good real deformation is maximal. This is an open question. Okay? There are some few results about this. The main difficulty, how to prove that some map germ from any dimension is a good real deformation. It's not easy to show that these are good real deformations, okay? I know this because we are trying very hard to find good real deformations. There are some known results. All asimple singularities of map germs from Rn to Rp, but here is n bigger or equal than p, as I told you before. You don't need for bigger here, just look for it equal, that you have the answers, and then you go to bigger dimensions, no change. Any asimple singularities from Rn to Rp have an M deformation, okay? All singular map germs of minimal cohunc and IA codimension 1, here is the A group, okay? This A should be an index here, but I did something wrong in the typesetting. This is non-result, okay? This result, I am going to show later, the references done by Cedinha and by Joachim Rieger from German. And an example that's done in the same paper, same papers, there are two papers. This is a simple cohunc 2, but does not have an M deformation. Of course that this guy is not in this situation because it's cohunc 2. Here is minimal cohunc. If I am from Rn to Rn, I have cohunc 1 situation. The references for this result, as I told you before, Rieger, Ruas, and Roberta Ticchi, and Ruas, Rieger, and Roberta Ticchi again. M deformations of a simple germ from Rn to Rn plus 1. Here I am in a different situation, okay? Not like that. But here I have a real deformations and invariants of map germs. Here is described in this situation. This result is described in the first paper, as far as I remember. And another situation that the good real deformations appear is in the paper of David Diamond and Washington Marar, a quite old paper, 1995, old for us, but for history it's not old, of course. If you consider from C2 to C3, it's different from the other situation. Here is, okay, here is from C2 to Rn to Rn plus 1. This is quite a generalization of the other result. C2 to C3, there are only two good real deformations. Tá? Okay, up to right-left equivalence, of course. We have S1 and the AGK, 2 in some situation, because here you can change the K. These are good, these germs have good real deformations here for any K bigger than 1, equal or bigger than 1, and here is S1 germ. Okay? And we see here in this paper, at present we have no example of a germ of minimal cohunc and positive amodality without an M deformation. This is also an open question, in fact, by now. And here is our work in progress, myself, Audicio, and Tassiana. Is there a cohunc 1 map germ from C3 to C3? We put only C3 to C3 here because it's the situation that we are working. You will see soon why. There is a good deformation, good real deformation in this situation, but positive amodality. Okay, this is not simple germ. Positive amodality is not simple germ. Okay? We don't believe that this question, we can find an example that has a good real deformation. We we think that the question here is no. But who can show? Okay, there is no one. To show that there is no one is not so easy to show an example. But here, even to work with examples is difficult, okay? These are open questions. We began to work with these questions to try to find an example in this situation, okay? One example of this. But we didn't find it by now. Why? Here I have, again from R3 to R3, the description of all simple singularities. Oh, these A classes of simple singularities of map germ from R3 to R3 of cohunc 1 are shown in the table 1. Cohunc 1 here, okay? And then these are simple. Good. If you go back, in these no results, all A simple singularities have an M in deformation. Very good. My question, okay, show me one good real deformation of this guy. You can say, they have, but to show one, we couldn't find an example that a good real deformation, really to show this is the good real deformation. We don't have. We tried. We are trying to do it. So we began to work with these guys to see, really, to point, this is the good real deformation of these guys. We couldn't by now, okay? So we are also working with the non-simple germ x, y, zeta 6 plus yz plus x zeta 2. This is not a simple singularity. Okay, it's not in this list. You can see here, the biggest is Z5, zeta 5. Okay, and just to give some properties of these guys. As I told before, from R3 to R3, we have swallowtails, we have double points, which are A21, and we have triple points. Okay, if you see here, all these simple germs here, they do not have triple points. It's a necessary condition to have a triple point. Oops, sorry. That you need to begin here with zeta 6, zeta 7. If you put zeta 5 and do the deformation, you don't find triple points. We know that there are no triple points in that guy, in that examples. Not the examples, but in that list, okay? So we are concentrated into study this guy, zeta 6 plus yz plus x zeta squared, and to describe something about this germ, okay? This is not the versal deformation of this germ initial. V and u are two variables, zeta 4 plus y3, but in fact this germ is a has codimension 4. We need the other two parameters to have a versal deformation of this guy. But if we include the two parameters with the total real versal deformation, it's quite impossible to work only with two parameters. To work with 4 parameters is a very, very complicated situation. Now I am going to describe a little bit about the topology of this germ, okay? Very useful situation. Okay, I look to the monogerms. Critical set, 2-dimensional, sigma is this guy. Okay, just to do the derivative of this guy, the 0 set you see here, okay? X, y don't appear because we have everything here. I have a y here alone, so I can write y in terms of this guy. So this is a smooth variety. Okay, 2-dimensional. As I told you before, the 2-dimensional is a smooth variety in the critical set. The 1-dimensional set, Audicio developed the algorithms we developed and he applied the algorithms to compute these guys. To compute the 1-dimensional set D1 FUV, we have 2 equations to describe these guys. And here we have the 0-dimensional set, the isolated critical points. 1, 2, 3 equations to describe. I have a U alone here, I have X alone here, I have Y alone here. Okay, this is very good to compute these guys. This, of course, came from this situation. I do 3 derivatives here, I have only U here, and you go on. Zeta 4 is the third derivative, and go on. Okay. We also have the B-germs. The D2 is a B-germ. Okay. One-dimensional, you have the equation here. Okay. Zero-dimensional, we have the equations. 1, 2, 3 equations. Okay. The 3 germs, we can have triple points. Oh, as I told before, zeta 6, we really have 1 triple point in this situation. Okay. And this here is the ideal that defines the zero-dimensional set. V here is the zero set of this guy, as usual in the notation. Here we compute the number of swallowtails of this situation, but real swallowtails. Oh, if it's real, we are looking to V and U, real parameters, okay? So we are trying to find the real parameters to describe these guys. I'm looking for good real deformations, even for M deformation of this guy. Oh, okay. Here we just need to look to this third generator, okay? And to understand this guy, we use the root discriminant. This is developed by Algicio. And the conclusion is the following. Okay, I'm looking to the zero set. We have real points, okay? But in different number, according to V and U, that we can see here, okay? Here we have U and V, okay, R2, a plane. And we are describing the regions that we have swallowtails, okay? The region U1 is here, We have 1 swallowtail, okay? Just a second. I will show you in the complex case how many singularities that appear in the situation, okay? I have it in the next transparency, probably, or 2 or 3 transparencies. So, in the region U1, I have 1 swallowtail. In region U2, I have 3 swallowtails. In fact, here, in the complex situation, there appear 4 swallowtails in the complex case. I will show you later. So, we do not have a maximal deformation in this situation. We cannot find 4 real swallowtails in this deformation of the map germ. Oh, if I include the other 2 variables that give me the versal deformation of this guy, maybe we can find it, but we cannot work with this. It's not an easy to compute these guys with 4 variables in the parameter space, okay? And you go from the region U1 to U2, you see that there are 2 swallowtails. This is the here I'm looking to the triple points, okay? Looking to the triple points, do the calculations, compute the ideals that define looking for the definition given before the triple points. And we have the generators that from here we need to work, this and this. And the number of real points A11, 111, sorry, we'll see in the next picture here. Here there are no triple points in this region. In this region here in the middle are no triple points, but in this situation we have 1 triple point, okay? Here we can find 1 triple point, but in complex case there is only 1 triple point? No, much more. I will show you. And now is the number of real A21. Okay, the same constructions did before to compute calculations. And here we have the number of points of type I21. 1, 2, 3, 4, 5 regions. Okay, 0, 2, 4, 1, and 3. Okay, there are no points A21 in these regions. 2, 4, and R3 and R4. R3 and R4 are these two regions here. 1 and 3. But I really thought that I had some transparency with the number of complex singularities here. I found it. 3 swallowtails. The maximum that we found was 2. 4 points A21. The maximum that we obtained in real situation is 3. And the triple points 1. Oh, we found triple points in the real situation, but not a maximal deformation by now. Okay? Even good real deformation, we have no idea because we didn't find a maximal deformation of this guy. We don't know if it has a maximal deformation. Okay? Okay. Now, I'm going to work about the real topology of the discriminant of this guy. This is why, because of the question of David Monde. Can we find a real good deformation of this germ? Okay? Our idea was to find this guy, but we couldn't. Here we have the singular set of the discriminant. Okay? The discriminant is a two-dimensional situation. And this is the singular set of the discriminant. So these are the singularities that are inside the discriminant. Okay? There is a blue line, a red line. Here is the triple point. We can really see it, the real triple point. Okay? We can see 2 points of type A21 in this example. Okay? And we have 1, 2, 3, 4. Oh, sorry, this is a swallowtail. No, the green one are the swallowtails. The swallowtails are formed by a blue line and a red line. Okay? It's quite easy to see. If you have a swallowtail, you need to have a cuspidal curve going to it and a curve of double points also forming the swallowtail. I will show you. I don't know how many time I have. What time is it? 10 minutes. So I will show you something later in the example. But now I am trying to compute the topology. Okay? The Euler characteristic. Oh, the Euler characteristic is the first thing that we can see. Vértices minus arestas minus faces. This is in Portuguese. Okay? Lines, faces, and vértices is 3 the Euler characteristics. On the other side, we have the rank of homology alternate sum. It's not the same number here, but the sum, alternate sum here, and the alternate sum gives the same Euler characteristic. The Euler characteristic is only 1. Using these results, we can compute the homology of H2, rank of H2. The rank of this guy is 2. Okay? This is not easy to compute if you don't have this kind of situation to work. Okay? We don't need to see pictures to understand these things. We need to see pictures to find the good real deformations. The first result was a situation here with 8 real points in the target. Okay? Here I have just 1 ball. But there are other U and V that give me 7 real points in the target. Okay? These 7 real points are these points, green and yellow here. Okay? It's interesting because with 7 points, we have an homology which is better than the other situation because of the distribution of the guys. Okay? Here I can see clearly the homology. Okay? With 8 real points, we have a wedge of 2 spheres. With 7 real points, we have a wedge of 3 spheres. However, the minor number of the discriminant minor number is 4. So, by now, we cannot say that this guy has a good real deformation. In fact, we believe that it does not have, but it's not easy to find. Just to show another example, zeta 4 plus yz plus xk zeta 2. This is one of the simple germs that appear. Okay, let's try to find the good real deformations of these germs. If you see here, there is one ball here, other ball here, okay? The homology, the real homology is 2, but the minor number of the discriminant is 3. So this is not an example of a good real deformation of this guy also, okay? This is another example. You see ball here, ball here. Here the ball does not complete because it goes to infinity here, okay? And this is the table of simple germs. It's the same simple germs that appeared before, but we have other invariants appearing here that we found. These are not described, these numbers are not described in the first list of simple germs done by Marara and Tari. Why not? Because that paper was written in 95. In 95, you had no computer machine sufficient to compute these guys. This is a kind of sophisticated situation, but we need a good computer. There are some examples, just to say, there are some examples that you cannot compute the guys, okay? So we have the minor numbers, the discriminant minor numbers associated with these guys. This is another invariant that I'm not going to talk about. And then we used to compute these numbers a different paper. It's given by Kevin Houston. Kevin Houston was a student of David Monde, but he's not working in singularity theory anymore as far as I know. But he gave a formula just after his PhD to compute the minor numbers, okay? And we used it to compute this table of simple germs, okay? Now, I stop here. Thank you.